This is chapter 15, capacitance and RC circuits. These are the questions and experiment video. Review questions for section 15.1. Question 1, a capacitor is made of two fill-in-the-blank layers of conductive material separated by an insulator called the fill-in-the-blank dielectric. Number 2, the ability of an insulator to support an electric field is known as the fill-in-the-blank dielectric constant. Question 3, find the missing values for the following circuits. These are presumably capacitive circuits, capacitive only circuits. For section A, we have 20 volts, 1000 microfarad capacitor, and we have to find the Coulomb value. Again, the Coulomb is the amount of electrons passing through a certain point in a circuit in 1 second. And we have a equation we can use to solve this, where the capacitance is represented by the C, and that is equal to Q divided by E. Q again is your coulombs, and E of course is your voltage. We are solving for Q, but we're going to, in this case, use the equation as it is, 0.0001 farads. That's your capacitor value. Again, you have to move the decimal point to the left, since we're talking about microfarads. We have to basically make it into farads, convert whatever value they give us, whether it's micro, pico, kilo. We have to convert that into single units, which are farads in this case. So we have 0.0001 equals Q divided by 20. Again, we have we don't have the value of Q, so we have to divide that by 20. We multiply the Q times both sides by solving the equation, and we multiply Q by the 0.0001. 20 is also divided. To keep solving, we divide the 0.001 by both sides, so 20 divided 0.001 equals to 200,000, and that is the value of Q, and that is our number of electrons passing through a certain point in 1 second. The number of that is the Coulomb value, so Q equals to 200k coulombs in this case. Section B, 10 coulombs are given, 40 volts, and we have to find the capacitance value of the circuits in this case. So we use the same equation. We have C in this case as your capacitance we're solving for, 10 coulombs as our Q value, and we have in this case 40 as our voltage. So 10 divided 40, we have 25.25, and we want that in microfarads again, as is asked for in the problem, section B. So we have to a micro is a million, so we move the decimal point to the right 6 spaces, and we get 25. Excuse me, we get 250,000 microfarads. So 250,000 microfarads. You can see that at the top right of the screen. 3B is labeled as 3A, but it's actually 3B. Moving on to section C, 200 coulombs. We're given 200 coulombs, 750 volts, and we have to find again the capacitor size in microfarads. And if you can see on the right, top right, section 3C, we have the same equation, where C is equal to, in this case, we're given 200 coulombs divided by 750 volts, we get 0.27. And again, we have to make that into microfarads, so we move the decimal point 6.6 spaces to the right. We get 270,000 microfarads, or 270k microfarads. Question 4, convert the following units. And we're given what looks like several capacitance units in farads, whether it's pico, micro, or farads, and we have to convert from one unit's measurement to another. First, section A, we have 6240 picofarads. That's 1 millionth of a millionth. That is 1 millionth of a millionth farad. So, and they want microfarad, which is 1 millionth of a farad. And all we have to do in this case is move the decimal point 3 spaces to the left. In this case, we're left with 6.240 microfarads. In the next problem, next section is B. We have 0.05 microfarads converted to picofarads. So we have 1 millionth of a farad units, and we have to convert to 1 million millionth of a farad unit, the picofarad. It's a very uncommon measurement, but we have to solve for it. So we basically move the decimal point 3 spaces to the right, and we get 50 picofarads as the equivalent. In the next section, C, 150 microfarads to be converted to farads or single units. We have to basically move the decimal point 6 spaces to the left to get single farad units, and we get in this case 0.00015 farads. And the other problem is the opposite. We get 0.005 farads, convert that into microfarads, and we simply move the decimal point the opposite direction to the right 6 spaces, since we're going from single units to 1 millionth of a unit. So we get we get 5,000 microfarads as the answer. Question 5, name 3 items that determine capacitance, and those are size of the plates of the capacitor, the distance between the plates, and the dielectric constant, or the material of the middle part of the capacitor. Question 6, list 6 sizes, or 6 types of capacitors. And we have several types of capacitors. They want us to name 6. Moving on to section 15.2 of the chapter. Questions. Number 1, can a capacitor that has a working DC voltage, again that's your your VW, no, your WB, working voltage of 25 volts. Let me repeat the question to make it clear. Can a capacitor that has a working DC voltage of 25 volts be used in a circuit that requires a working DC voltage of 10 volts? Explain your answer. What I have here for the answer is your working voltage is the maximum voltage that the capacitor could withstand, so a lower voltage is always okay. For example, a working voltage of 120 volts capacitor should be, or a working voltage for a 120 volt circuit should be about 169, 170 volts. Since the average of a 120 volt circuit does vary, and it could go as high as 170 volts, so your capacitors should be rated to handle up to 170 volts. That is on a common AC circuit. Given the capacitance for the circuit below, as you can see, find the time constant for the following, The question reads again, give the total capacitance for the circuit or for the circuits below. And as you can see, this is a series. The first picture is a series capacitor circuit. Capacitors are in series, and the formula for that is right below that, where 1 over capacitance total equals to 1 over, in this case, 30 microfarads plus 1 over 50 microfarads plus 1 divided 75 microfarads. And to add, we have to find the least common denominator. In this case, it's 150. So we add. Once we solve for the least common denominator, in this case we have 5 over 150 plus 3 over 150 plus 2 over 150. You add that, it gives you 10 over 150, and it's simplified to 1 over 15. So you get 1 over 15 equals to 1 over CT, or total capacitance. So to convert that, to solve that for CT, we basically divide 1 by 1 over 15. In this case, gives us 15 microfarads. And that is the answer for that problem, A. Moving on to B, we have capacitors in parallel in a circuit, and we have to solve for the total capacitance. In this case, all we have to do in this case is add those capacitors, since voltage drop is presumably the same throughout those capacitors. However, we have to make those values equivalent. Notice that we have in the first circuit to the left, we have picofarads. In the second in the second leg, or in the second capacitor, we have picofarads again. The third capacitor, we have microfarads. So we have to basically make them all the same. In this case, I chose to go with making them all microfarads. It's a smaller, more manageable amount or conversion unit to go with. And we basically move the decimal point to the right 3 points or 3 spaces on the first capacitor and the second capacitor, and we get 510,000 microfarads and 490,000 microfarads. We add that with 0.0005 microfarads, and we get, ultimately we get 100,000.5 microfarads, and that in reality is about 0.1 farads. Question 3, find the time constants for the following circuits. The first one, we again have to work with one type of unit. We have to make them, in this case, into farads. They are given in microfarads, but we make them into farads to solve, because the equation that we are given, where T, the time constant equation where T equals R times C, we have to have farads, single units. So we convert those, as you can see on the lower left. 500 microfarads is equal to 0.0005, and we have 2,500 ohms of resistance. We plug those into the equation, which again is T equals to R times C. We get 1.25. That is the time constant. That is a time unit, 1.25 presumably seconds. Section B, we have 225 microfarads, which is the same as 0.000225 multiplied by 3200 ohms. We get 0.72 in seconds. The third, section B, 67 microfarads, is the same as 0.000067 times 180 ohms. We get in this case that you can't see that on the screen, but we get 0.01206, 0.0106, excuse me, 0.01206. That is the amount of seconds, 0.01 seconds more or less. Review questions for section 15.3. Number 1, using the list of words given, fill in the spaces to make the statement true concerning the equation for capacitive reactance. And the statement is, in the equation, XC equals to 1 over 2 times pi times frequency times capacitance. The capacitive reactance is, and the answer for this one is XC. Secondly is C equals capacitance in farads, and F equals the frequency in hertz. Question 2, define capacitive reactance, and it is the opposition to alternating current by capacitance, or better said is the opposition to voltage, which in turn is the opposition to current by capacitance. Number 3, find the capacitive reactance in the circuit shown. We have a series circuit, an RC circuit, with a capacitor of 150 microfarads and a resistor of 1 kilo ohm. To solve, we use the formula for capacitance, which is 1 divided by 2 times pi times frequency times capacitance, which in this case gives us ultimately 0.05652, and that is in ohms. Question 4, find the following values using the circuit shown. Portion A, find the capacitance, or Z. For that we use the variance of the Pythagorean theorem, where Z equals to the square root of the squared resistance times, or excuse me, the square root of the resistance squared plus the reactive or capacitive reactance squared. And in this case we have 15 squared plus 12 squared, or 369. We square 369 and we get 19.20 ohms for your impedance. Again, your impedance is the combination of reactive resistance and the resistive value in ohms. It is a vector sum, which we can do with, again, with the Pythagorean theorem. Section C is to find the cosine theta, which is again the vector cosine theta, and that would be gathered by multiplying your resistance times your reactance, in this case 15, divided by 19.20, and we get cosine theta of 0.781. You punch that into your calculator, make sure the angle mode is in degrees, not in radians or radians. Make sure it's in degrees, and you should get 39 degrees. In most calculators, all you have to do is punch shift and then cosine -1 or cosine to the first power, and that will give you your theta in degrees, in this case 39. So portion C is your current, C, and your current in this case is, your current leads, that is the answer, it leads the power or the voltage, or E, by 39 degrees. Jumping on to project 15-2, building a tunable electronic organ. And this lab is an example of a two-stage amplifier connected to a astable, or connected as an astable multi-vibrator oscillator circuit. You will learn about amplifiers and oscillator circuits later in the textbook. For now, just remember that an oscillator circuit causes a repetitive AC cycle. The repetitive AC cycle will cause a tone to be generated out of the speaker. The part of the circuit that correlates to this chapter is the RC circuit. Look at the bank of variable resistors connected to a set of 7 momentary push buttons. Each of the variable resistors is set to a different resistance value. When any push button is pressed, the corresponding variable resistor forms an RC circuit with capacitor C1. Since each of the variable resistors are set to a different resistance value, a different time constant is created for each push button. The various time constants each create a different tone in the speaker, and you can follow the circuit as shown. The parts are also described on the middle right, and what the circuit may look like is at the bottom of your screen. The summary for this chapter is: 1. Capacitance is that property of a circuit that opposes any change in voltage. 2. A capacitor is a device that temporarily stores an electric charge. It is made of 2 plates of conductive material separated by insulation, called the dielectric. 3. Capacitance is measured in farads. Commonly used units are the microfarad. The symbol is shown, and the picofarad, symbolized as PF. Number 4, factors affecting capacitance are: A, distance between the plates, B, plate area, and C, dielectric material. 5, there are many types of fixed and variable capacitors. 6, the RC time constant can be found using the equation time, which is in seconds, equals R in ohms times C, which is in farads. Number 7, the formulas for capacitors in series and parallel are as shown, where capacitors in series is 1 divided by the capacitance total equals to 1 divided by capacitance 1 plus 1 divided by capacitance 2 plus 1 divided by capacitance 3, and so on. Or a shortcut, when only 2 capacitors are in series, you can use the capacitance total equals to capacitance 1 times capacitance 2 divided by capacitance 1 plus capacitance 2. For capacitors in parallel, you use the formula capacitance total equals to capacitance 1 plus capacitance 2 plus capacitance 3, and so on. Working voltage is the maximum voltage that can be steadily applied to a capacitor without creating an arc, sometimes referred to WV. 9. Capacitive reactance, or XC, is the opposition to the flow of an AC resulting from capacitance. 10. The formula to find capacitive reactance is shown at the bottom left of your screen, where XC equals to 1 divided by 2 times pi times frequency times your capacitive size in farads. Number 14, the impedance in a series RC circuit could be found using the formula, which is a variation of the Pythagorean theorem. Z equals to the square root of R squared plus XC squared. The phase angle can be found in an RC circuit using the formula cosine theta equals to resistance divided by reactance. 16. When a resistor and a capacitor are in parallel, the branch voltages are the same, however the branch currents will be 90 degrees out of phase with each other. Number 11. The true power can be found with the formula true power equals to current times voltage times cosine theta. Number 12. Apparent power can be found with the formula apparent power equals to current times voltage. Number 13. Power factor can be found with the formula power factor equals to true power divided by apparent power. Now to jump into the test your knowledge questions. Define capacitance. In this case, capacitance is the property that opposes a change in voltage in a circuit. Number 2, what safety precautions should be taken when working on a radio or TV capacitors? And it is to discharge the capacitors before you handle them. Discharge them with a screwdriver that might be insulated to a high voltage. Discharge them to a good ground, or to, at the very least, the metal frame of the device. Make sure it is the metal frame, and make sure you test the capacitor, make sure it is discharged with a multimeter. Number 3, with respect to dielectric constant, the larger the number, is it better or worse that it supports an electric field? And in this case, it is the better. It supports the electric field. Capacitance is determined by A, dielectric material, B, plate area, C, distance between the plates, or D, all of the above. The answer is D, all of the above. 5, the time constant of an RC circuit is equal to, and that would be resistance times capacitance, or R times C. Number 6, determine the total capacitance for the next few capacitors. 2 capacitors connected in series with values of 680 microfarads and 200 microfarads. For this first problem, problem A, we can use the shortcut formula where CT equals to C1 plus C1 times C2 divided by C1 plus C2. So using that formula, we plug in the values of 680 microfarads and 200 microfarads, and we get ultimately 154.5 microfarads. For problem B, 4 capacitors are connected in parallel with values of 25 microfarads, 60 microfarads, 2 microfarads, and 4 microfarads. Again, pay attention to whether the circuit is in series or parallel. In this case, we're talking about parallel, and we have to use the formula CT equals to C1 plus C2 plus C3 plus etc. And in this case, we get 91 microfarads when you add those up. When 5 capacitors are in parallel, again, plug in all those values in an addition. Make sure they're all the same scale or the same prefix. They have to match. If they're not, you have to convert them so they match. In this case, they all match. 1150 picofarad, 97 picofarad, 130 picofarad, 1240 picofarad, and 50 picofarad. You add those up linearly and you get 2667 picofarads. The symbol for capacitive reactance is XC, of course. It is measured in ohms and can be found using the formula XC equals to 1 divided by 2 pi times frequency times capacitance in farads. The capacitor has a value of 0.1 microfarads. Find its reactance value at the following: A 50 Hertz, B 100 Hertz, C 1000 Hertz, and D 10 Hertz. And I have worked those problems out in the screen towards the bottom using the formula XC equals 1 divided by 2 times pi times frequency times capacitance. Plugging in what we already have, which is the value of your capacitance, in this case 0.1 microfarad. You use also the hertz that are given in A, B, C, and D. Plug in those factors in. You know your pi, you know you have to multiply that by 2, and you have to multiply all those and then divide 1 by all those products, and you ultimately get, for A, 318.5 kilo ohms. For B, you get, using those using 100 Hertz, which is the only variable that changes. Plug in your 100 Hertz into the formula, you get 15.9 kilo ohms. For C, you plug in your hertz, your frequency, the only variable in the formula, you get 1.59 kilo ohms. And there's a pattern here between B, C, and D, and we're using multiples of 10 for your frequency, so your answers are going to be in a pattern. In this case, for C, we get 1.59 kilo ohms, and finally for D, we get 159.23 kilo ohms. Question 9 is, as capacitance increases, then capacitive reactance decreases, and as frequency increases, capacitive reactance also decreases. To continue, match the following terms with their correct definitions. You have them shown on the screen. Number 10, resistance divided impedance is your cosine theta. Number 11, current times your voltage equals your apparent power. And then that is incorrect. Number 11, your current times your voltage is your true power. And number 12, your current times the voltage times your cosine theta, which is your vector for the resistive total, both capacitive and resistive. That is your apparent power. And that is A. 12 is A. So omit or disregard what you see on your screen. Number 11 is C. Number 12 is A. 13. We have a version of the Pythagorean theorem, which is the square root of resistance squared plus your capacitive reactance squared, and that is your impedance. That will give you your impedance, or Z. So 13 equals to E, as you see on the screen. 14, true power divided by your apparent power is B. It is your power factor. A series circuit has 300 ohms of resistance and 0.1 microfarads of capacitance. It is connected to a 50 volt 400 hertz source. You will find for this problem A, your reactive capacitance, or your capacitive reactance, better said. B, your impedance, or Z. C, you will find or attempt to find the voltage drop at your capacitive reactance or at your capacitor. And your power, D, your voltage drop at your resistor. You will find E, which is your current, and F, theta, for the circuit in series, which is given up top, 300 ohms of resistance and 0.1 microfarads of capacitance with a 50 volts 400 hertz power source. For this first problem, we use the formula for capacitive reactance, which is XC equals to 1 divided by 2 pi frequency capacitance, and that ultimately gives us 0.25 ohms. Plugging in again the values that we already are given. So to find our impedance, we use the Pythagorean theorem, which is the square root of the resistance squared times, the square root of the resistance squared plus the capacitive reactance squared, which in this case is 0.25 squared plus 300 squared, or 0.0625 plus 990,000. You add those up, and squared gives us 300 ohms. C, the voltage drop at XC, your capacitive reactance. And for that, you can see it being worked out. An attempt of it being worked out is towards the bottom middle of the screen, where you have XC equals 2.25 ohms. Right below that, you have
EXC, which is your voltage drop at XC, which equals your current times your resistance. In this case, we already have 0.16 amps for your current, and we have 0.25 ohms as your resistance. You multiply those, you get 0.04, which is the same as 40 millivolts. For question D, what is the resistive voltage drop? In this case, we work that out by multiplying the 300 ohms that we already know for the resistance times our amperage, which is 0.16 amps. We get 48 volts. Our amperage, how did we get that? I get that by multiplying using the Ohm's law formula or equation, where current equals to voltage divided by, in this case, impedance, which is the resistance in the circuit. And we have 50 volts divided by 300 ohms, which is 0.16 amps. And finally, theta, I found that out by getting the cosine, which is equal to the power factor, or resistance divided by reactance. Resistance divided by impedance, which in this case is 300 ohms divided by 300 ohms, which in this case is 1. So 1 is the theta of 0 degrees. When you punch that into your calculator, you punch cosine theta, or cosine to the negative first power, you get 0 degrees. Question 16. The frequency of the currents in a circuit is 1000 Hertz. What are the reactance values of the following capacitors? As you can see, you have to convert each capacitor value into a single farad unit, or into the farad units. They're all in microfarads. Convert them into farads. You have to move the decimal point from each value 6 spaces to the left, and you get the values shown on your screen. On the top right, you use those values to plug those into the formula for capacitive reactance, which is XC equals to 1 divided by 2 times pi times frequency times capacitive size. And in each case, for example A, I get 318, as you see it worked out. For B, you get 1592 ohms. For C, you get 3184 ohms. For D, you get 15.9 kilo ohms. And for E, you get 159.2 kilo ohms. And that concludes this chapter's questions and experiment. This again was chapter 15, capacitance and RC circuits, question and experiment. Congratulations, you have earned this electronics course rank.